Next up, let's take a look at indexer properties. Indexer properties are interesting to us, especially because they facilitate the creation of something called property bags. Property bags is a very important feature under the covers of the AF Core framework. For example, AF Core uses it to allow us to implement direct many-to-many relationships. We shall look into this in more detail later on, but during one of the upcoming demos, we shall also take a look at how we can use property bags to allow us to implement a tagging feature that CardRock can apply to its customers. But let's get started by getting an understanding of what indexer properties are. To put it simply, indexer properties are properties which are backed by an indexer on our entity class. Indexers, as you may know, are not specific to AF Core. They're used extensively inside the .NET framework to facilitate indexing of such things as collections, and we can also use them within our own applications. But when it comes to AF Core, we can also use them to create something called indexer properties. These indexer properties provide us with a way of adding additional properties to our entity types without changing the code of the underlying class. We shall soon see this in action during the upcoming demo. So in order to create an indexer property, we first need to create an indexer on our entity class just like we would for any other C# class that we wanted to make indexable. And that is exactly what an indexer does. It allows class instances to be indexed in the same way that, for an example, an array is indexed. But in relation to AF Core, the most interesting aspect of using indexers is that they allow us to create indexer properties. And so we will not be spending time on diving into how indexers work. But if you're not already familiar with them, I suggest you take a look at the official Microsoft documentation. I'll provide a link at the end of the module. In the following discussion of indexer properties, I'll assume a basic familiarity with indexers. Before we dive into the demo, let's consider an example. Take for example our customer entity. If we were to implement an index on that, we would add code lines similar to what we see here. The first thing that we would do is to create a dictionary of type string and object to contain our indexer properties. And following that, we have the implementation of the indexer, which we'll use to access these properties. Please note that we use a dictionary of string and object here, since as per the newest version of the .NET framework, this is the only type supported for indexer properties. After having added the indexer property to our entity type, we need to set up the actual indexer property. We do so in the unmodeled creating method of our database context, using code like what we see here, where we set up two indexer properties on our entity using the indexer property method by first applying the generic type parameter and then passing in the name that we want to use for the property as string input to the method. First we set up a datetime property called last updated and then a string property called consumer type. In the upcoming demo, we'll look at how to interact with these properties. But before we get started on the demo, let's just take a look at a special case of using indexer properties. Entity types that only contain indexer properties are called property bags, and the most common use case is probably one where we might not even realize that a property bag is being used. That is when we create a direct many-to-many relationship, which means that we are creating the relationship without introducing an intermediary class to represent the so-called join entity. In that case, AF Core creates a property bag entity to function as a join entity for us. And when in our code we are selecting data from the collections on our entities that make up this relationship, AF Core will use the property bag it created for us to create the join needed to get the data on the database. But apart from such scenarios where indexer properties are used behind the scenes by the AF Core framework, there are also certain cases where we might want to create a property bag entity ourselves. Even though we might not often run into needing indexer properties for ourselves, cases do exist. And property bag entities are also worth knowing about because they help us understand what AF Core is doing for us to facilitate direct many-to-many relationships. An example of where we might want to create a property bag entity ourselves could be that the CardRock team wants to provide the option of adding certain tags to customers, such as what type of customer they are and potentially a fixed discount rate for them. If for some reason the structure of this data is maintained outside of our AF Core model, for example in a JSON settings file, creating a property bag for this data would allow us to interact with it nonetheless. Property bags are also set up in the unmodeled creating method of the database context, and it's done by defining a shared type entity like we see in the code here. And once again we see that the type for the indexer property is set up to be a dictionary of string and object. The first parameter to the shared type entity method is the name of the property that we would like to define. In our case, we call it tag. Secondly, we passed in an anonymous function where we set up the properties that we would like to define on the type. Here we define an ID, a customer ID, a nickname for the customer, and finally a discount rate property. Note that by convention, the ID property will be mapped as the primary key column on the table that will be created for the tag type that we are creating here. The customer ID, on the other hand, will not be mapped as a foreign key relation to the customer's table, but we can still use it to create an indirect link between a tag and the customer that we want it to apply to. Also note that even though we do not have an entity class that maps to this new type, and that the properties it has are therefore not mapped to any properties on an entity, ifcore will not create shadow properties for these, but rather it creates indexer properties for them, even though we have not explicitly defined them as such. The last bit of code that we see here sets up a collection that we can use to access the contents of the tags table. This collection will be defined on the database context class, and we create it by using a call to the set method, where we pass in the generic type parameter as a dictionary of string and object, and we pass in the value tag for the name of the share type entity that we want to be able to query. In the example that we see here, all the properties for the property bag are hard-coded. In a more realistic setting, we would probably have the specifications for the tag entity defined elsewhere, such as in a JSON settings file. That file would then contain the name of the table and the type of columns that it must be made up of. That information could then be processed in our onModel creating method to create the table. This would require us to read the name of the table from the settings file, and then looping through the information about all the columns, setting them up one by using the non-generic overload of the property method, which takes a type and a string for the property name as input. In our case, where we know everything about the table to begin with, we could probably just as well have defined an entity class for it, but the code in the example illustrates what needs to be done in order to set up a property bag. So let's get started and take a look at mapping indexer properties. We're now back inside Visual Studio, and we're looking at the customer class. As you may remember from the slides, we had to add an indexer to the entity classes where we want to define indexer properties. That is what happens here for the customer entity. The first line of code here defines the dictionary, which we will use as a backing field for the indexer. Notice that just like in the slides, we set up the dictionary to be a dictionary of object and string. The next bit of code here implements the actual indexer. We'll be using this to store indexer properties on our customer instances. The indexer is implemented using the this keyword as we would do on any other C# class. Just notice that for the indexer to be used with indexer properties, the signature of the indexer must be indexed by a string and return a value of the object type. Now let's head over to the database context, where the actual indexer properties are set up in the onModel creating method. If we take a look at this bit of code here, where we set up the customer entity, we can see that these two lines of code has been added. The first one uses the index property method to create a datetime indexer property, just like we saw in the slides. And just like in the slides, we call it last updated, and the only difference here is that a call to the hash default value method has been added, which stipulates that the field must have a default value of the 1st of January 2020. This last bit has just been added to stress the fact that indexer properties can be set up with default values or as computed columns, just like any other property that we set up on our entities. In fact, the indexer property method returns the exact same property builder type as the property method that we have used several times by now does. Below this, we add another indexer property, which is a string property called consumer type. Before we start actually interacting with these new properties, we need to create a code first migration for them and apply it to the database. We'll do so here in the package manager console, where we'll add a new migration called indexer properties. If we take a look at the migration file that this creates, we can see here that there's nothing to indicate that the new properties that we're adding are indexer properties. Rather, they are set up using the add column method on the migration builder, as we would expect for any new properties that we explicitly add to our entity classes. And the default value of the last updated column is set up to be the 1st of January 2020 as we had specified. Also notice that because the last updated property is a datetime property, ifcore makes it non-nullable. If we wanted to make it a nullable field, we would have had to define the property as a nullable datetime object. If we now apply this migration to the database by using the update database command in the package manager console, we can take a look at how these new properties are implemented on the database. We can do so here in the Server Explorer. And if we take a look at the customers table, we can see that our two new properties have been added as columns to the table. If we look at the properties for the two new columns, we can see that ifcore has inferred the customer type as an nvarchar type column. We may note here that the length is set at -1, but that simply indicates that this is an nvarchar max type, meaning that it has the maximum length of the nvarchar type. And if we look at the last updated column, we can see that it has been inferred as a datetime2 type column. If we open up the table definition for this table, we can see the create script that is used to create the table on the database. And here we can see that the two columns have been set up exactly like we would expect any column of their type to be. So once again, nothing indicates that we're dealing with an indexer property. But once we start to actually interact with these properties in our code, the difference starts to show. Because unlike other properties, we cannot access these properties directly from our customer entity. Before we start to do so, let's just quickly take a look at the contents of the customers table. So as we can see here, our two customer entries now have two new columns, the consumer type column and the last updated column. As we would expect, the last updated column for both entries contains the 1st of January 2020, whereas the consumer type column contains null values, since we did not specify a default value for this column. So now let's head over to the program class of our console project and take a look at how we can interact with these new properties of our customer class. So just like we saw with shadow properties, the first thing that we do is to fetch the first customer from the customers collection on our database context. But unlike when we were working with shadow properties, we don't have to make the query a tracking query. So to illustrate this, we'll try to fetch the customer using a non-tracking query. After having fetched the customer, we used the indexer property on the customer class to first fetch the last updated property, which we cast to a datetime object. And after this, we fetched the consumer type, once again using the indexer, and cast it to a string. The next few lines of code add data to the dictionary that our indexer gives us access to. The first line here attaches the customer to the change tracker on our database context. This is necessary since the customer's instance was fetched using a non-tracking query, and we now want to change the values of the indexer properties that have been defined on it. If we do not attach the entity, subsequent calls to save changes will simply disregard all our updates and nothing will happen in the database. After this, we change the last updated entry to be the 1st of January 2022 using the indexer, and then we set the consumer type to be big spender. The third line of code adds a new entry to the dictionary called not defined, passing in a string value saying that this will not be saved on the database. The reason why this line of code won't throw an exception is that, as we have stated a few times, the indexer on the customer class works like any other indexer, which will allow this kind of assignment. But because we haven't defined any string indexer properties called not defined on the customer entity, ifcall will simply ignore this entry in the dictionary when we call save changes on the database context. Just like we see here, where we save the changes that we made to the customer entity using indexer properties. Once we've saved the changes to the database, we retrieve the updated customer once again. This is mostly to illustrate that, like we saw with shadow properties, we are also able to use the ef.property method to fetch indexer properties inside of a link statement. In the following lines of code here, we once again change the value of the last updated property, this time setting it to the 31st of December 2022, and finally we fetch the customer once again. Now let's run the code and see all of this in action. So first of all, we fetched the first customer from the customers collection. And if we now advance the debug a few steps, we read out the values of the last updated date and the consumer type indexer properties. As we can see here in the watch view, the last updated date is set to the default value of the 1st of January 2020, and the consumer type is null. This is not surprising since we have yet to add any data to these properties. So if we advance the debugger step, we've now attached the customer entity that we just fetched to ifcall's change tracker, and we can start updating it. So let's move over the next three statements where we add data to the indexer on our customer entity. If we now look in the watch view and expand the customer entity here, we can see the underlying dictionary that we use to map the indexer properties, and we can also see that it has three values in it. These are the consumer type, the last updated date, and the not defined entry, which will not be saved on the database. So let's advance the debugger step and save the changes to the database. Having done that, let's just quickly fetch the updated customer in the following link statement where we use the ef.property method. If we now look at the returned entity in the watch view, we can see that the customer now has a consumer type of big spender and a last updated date which says the 1st of January 2022. So both fields have been updated just like we would expect. If we head back to the Server Explorer to take a look at the contents of the customers table, we can see that these changes have been applied. Just to show that we can continue working on our customer entity, let's advance the debugger to set the last updated date to the 12th of December 2022 and save the changes. And if we now go back to the Server Explorer to take a look, we can see that this change has also been applied. And if we return to the code and fetch the customer once again, we get a customer back with the new last updated date, as we can see here in the watch view. Also notice that we no longer see the not defined field, since this was not mapped as an indexer property, therefore it only lived on our in-memory instance and was not persisted along with the other entries on our indexer.